Shamika Spencer with NASEO, and I want to welcome everyone to today's webinar entitled Electromagnetic Pulse and its Impact on the Electric Power System. Before we get started, I want to review a few housekeeping items and let you know how you can participate in today's session. First, we will be recording today's webinar, and we'll be sending out a follow-up email to all participants with the link to the recording once it has been uploaded to the NASEO website. Second, you joined today's webinar listening. If you joined today's webinar listening through your computer speaker system by default, you will be able to hear the presentation, but you will not be able to ask any questions. If you'd like to call in using the phone, just locate your audio pane and select use telephone, and then the system will provide you with a dial-in information access code so that you can ask questions. Finally, to avoid background noises, everyone has been placed on mute. At the end of the webinar, we will have time for a Q&A session. If you have any questions, please, or comments, you can type those into the chat panes or the question panes on the control panel. Also, you can use the hand raise icon on the control panel if you want to indicate that you want to be unmuted so that you can ask your question directly. So now I want to introduce David Gibson, who's the co-chair of NASEO's Energy Security Committee, and he's going to provide the welcome and opening remarks as well as the introductions for today's webinar.
Welcome, everyone. Thank you for joining NASEO's Fuels and Grid Integration and Energy Security Committee's webinar on electromagnetic pulse and its impacts on the electric power system, featuring John Ostrich and Rob Manning, who I'll introduce in just a moment. Protecting the nation's electric power grid and ensuring a reliable and affordable supply of energy are top priorities for the electric power industry and the nation. The power grid is a complex, interconnected network of generation, transmission, distribution, control, and communication technologies that can be impacted by natural events, including severe storms, earthquakes, and geomagnetic disturbances like those caused by solar flares and by malicious events like cyber or physical attacks. In today's webinar, we will hear from John Ostrich and Rob Manning. John Ostrich is a program manager, risk and hazard analysis, infrastructure security, and energy restoration division, the Office of Electricity Delivery and Energy Reliability at the U.S. Department of Energy. John Ostrich's bio involves, he's a systems engineer who has analyzed and managed a variety of projects related to energy assets and systems, including software development. He's worked for or supported DOE since 1992. Prior to supporting DOE, Mr. Ostrich was an intelligence analyst with a focus on military systems, conventional and nuclear, in both China and in USSR. In 1992, he wrote and published an article predicting a major attack on the United States and calling for a program of enhanced active and passive defenses. Currently, Mr. Ostrich is a program manager of risks and hazards analysis. In this role, he identifies, prioritizes, and then manages a variety of projects addressing threats and hazards to energy systems, electric as well as oil and gas. A recent focus has been leading DOE efforts to address GMD and EMP, and Mr. Ostrich also represents the DOE in interagency policy discussions on all mitigation activities. At this point, I will turn it over to Mr. Ostrich for his presentation, and then after that, I'll introduce Rob Manning, and again, we'll take questions at the end of both of the presentations.
Okay, thank you very much, David.
Okay.
Can you hear me okay?
Yes.
Yeah.
Okay, very good. And you know, that last point that David made, we're actually in the last couple of years, we both have been on the mitigation task force. David is nicely agreed to join. We had nominated him at DOE to be a state rep on the mitigation task force in the last 2 years. He has served in that capacity and is just wrapping up his tour. So thank you, David, for that. Shamika, if we could go to my next slide, shows my agenda for the day. I'm going to go very quickly so we can have Rob spend most of the time during the webinar. So that's what I'm going to cover today. Really go a little bit into how we came up with the strategy, action plan, and then talk a little bit about some of our activities before I hand over to Rob. So we can go to slide number 3. So back in December 2015, Secretary of Energy decided that Department of Energy needed to have an EMP strategy that would address the risk to the electric grid specifically. It would not simply be a report that would just sit on the shelf. It was supposed to be actionable. So it was to be followed by a realistic action plan that could be implemented. I was directed to develop that strategy and that action plan. Same time, interestingly enough, and I think independently, EPRI decided it should do some research and take some action on the EMP risk also. So Rob Manning and I connected, got together in January 2016, and developed that joint DOE industry EMP Resilience Strategy. Then we discussed and decided it would be best for DOE and for EPRI to develop separate action plans, since government industry focus would be different, even though we were working towards the same agreed upon goals. We wanted to ensure independence of government and industry on this. So DOE and EPRI worked closely together, though, developing each of the plans. We wanted to minimize duplication of effort, but we've kept each other informed on progress and issues on a regular, frequent basis. Now, it's not to say that EPRI and DOE haven't investigated this problem before, because we've had many meetings before this. This is just certainly cranking up the efforts on this. So, in fact, in January 2016, as we started the strategy, we had the Idaho National Lab finish some EMP research for us, and they actually published a DOE-funded study on mitigation and protection strategies, specifically on EMP, and that's published on INL's website. So as I said, DOE and EPRI developed this joint strategy. We released it in jointly. We released it in July of 2016, and then we developed our action plans. DOE's was finalized a little bit later than EPRI's. We published ours in January 2017. And again, each plan is separate, but we do have a stake in EPRI's plan. We have funded WAPA, the Western Area Power Administration's participation in that plan. Let's go to the next slide, please, Shamika. So here's the 5 goals in the EMP Resilience Strategy. And again, this is the joint strategy, so EPRI as well as DOE have these same goals, those 5 strategic goals. We really felt that the Department of Energy had the major role to play in Goal 1. In fact, we have 19 action items, and half of them have to do with the first one, which is understanding of the EMP question. So that's really my mission: find out what's known and to try to share that with Rob and with Randy Horton, who's leading his effort. Because much as is known already about EMP effects, coupling impacts, mitigation, protection. Tremendous amount of work has been done by DoD, so we're all meeting with them as frequently as we can. In fact, we have a meeting coming up in May where we're meeting with the Defense Threat Reduction Agency, EPRI and DOE both. But of course, their focus has been on their forces, not on the electric grid. So we saw, industry and DOE both agreed. Industry's role is really most critical in the second goal. They're really determining what's critical. We have a small role in that. The utility companies and industry themselves modeling their system, understanding and really know best what's critical. And also in enhancing response and recovery, that's more of an industry goal, although we have a role in that as well. So our main goal really is to improve the science and of the understanding of EMP. And then, of course, number 5 there, that last goal, is to make sure everybody shares it, because it's hard to share a lot of this since it's classified. So we're working on EPRI to try to get out some unclassified information on this in terms of the waveform, the effects, what the environment looks like. Let's go to slide 5. Okay, so this is, we can get into detail on the action items. You can certainly look at the plan, it's online. Really what I wanted to talk about is, kind of how we came up with that. And, we started with really reviewing recommendations the EMP Commission had come up with for the power grid, and they had a number of them, and some other credible studies and entities also. So we looked at that, started as a baseline, brought experts together to work on our task to do this, including somebody from the EMP Commission, to help us really identify these, prioritize them, and justify each action. We came up with probably about 50 actions, narrowed it down to 19 that went into the plan. So that's how we did it. And like I said, we got together a lot of people, got a lot of input from experts. We had to end up deciding, but had a lot of good brainstorming to determine what could be done, and then determine the 19, which is in our action plan. We'll go to slide number 6 next. A couple other things that we've done. So this Mission Executive Council, that was established this year, and actually it was late last year we established it. And this is a group that's the Department of Homeland Security, Department of Energy, Department of Defense, and the intelligence community. Those 4 groups get together and discuss topics of interest to all of them. The first one was defending space assets and really looking at threats to satellites and communications. That was done. The report was put out. I believe that's classified. The second thing was looking at the threats and the risk to microelectronics, which of course has an EMP component. That one was finished up recently. The third topic that 4 agencies are looking at is EMP. So we are working on that right now, looking at a strategic framework, putting out a white paper that's going to show unclassified. This is where where the government views what this threat is and really what the critical factors are. Some of the other things we're going to look at is some of the gaps and areas where we have to do some more work. That's not going to be published because we don't want bad guys to know where we think we have weaknesses. Some of the other things we've done recently is, like I said, in January, January 2016, INL put out a study for us on mitigation and protection strategies. They're currently working on a grid vulnerability report for us on EMP, very detailed, much more detailed than the last study. We have Los Alamos. We're working with DHS to really look at what scenarios should industry be worried about. How big a bomb, what altitude, things like that. So you can't look at every possible scenario and plot it out and model it. So we're trying to narrow that down to a handful or less, maybe a couple on some work there. Excuse me. Also done many briefings and discussions like this one with industry. I try to share whatever I get my hands on with EPRI, and including the classified work, because we have some cleared people there we can get the information to. The white paper on EMP will be unclassified, will be out soon, certainly by the summer. EPRI and DOE are then going to work on unclassified waveforms so that we can get that out to folks who need to model and look at what impacts could be to your systems based on those probable scenarios, and then also an unclassified environment. Also to let you know, the Strategic Transformer Reserve Report is out. That's on our website. Last thing just to mention is we do have a track program, Transformer Resiliency Advanced Components Program. There's information also on DOE's website, and that 4 awards have been made already to look at new designs for transformers, to really develop and design more flexible ones, the spares that can have adjustable impedances and all sorts of adjustable components on them. So it's not a spare, but it's more a standardized spare. And a bonus would be easier to move. That's not the priority of it. It's really flexibility. Last slide, we'll go to number 7. And this is our plan forward, is just to begin implementing that EMP action plan and to continue working with all of our partners, DHS, DOD, other folks in Department of Energy, the intelligence community, industry, and also non-governmental organizations. What I'll say is the last thing about that workshop, we're trying to do an annual one. We may not, but we're still going to continue to have small group discussions like this, as well as larger group discussions in the future. So that's all I have for my presentation. I wanted to make it short so that Rob could get into a lot of details on what EPRI is doing. And hopefully I'll be available for questions when we're done. I'm on battery computer, so hopefully it won't burn out. So if I'm not, you can certainly let Shamika know the questions. I can try to answer them later. So thank you very much, and turn it back to David. I think he's going to introduce Rob.
Okay, thank you, John. That was a good overview. And for those of you that have some questions, hang on a little bit, and we'll go through Rob's presentation first, and then we can come back to Q&A at the end. Rob Manning is Vice President of Transmission and Distribution for the Power Delivery and Utilization Research Sector at the Electric Power Research Institute, EPRI. He has overall management and technical responsibilities for the annual research activities conducted by EPRI's transmission and distribution programs in collaboration with its global membership. Prior to joining EPRI, Mr. Manning served as the Executive Vice President and Chief External Relations Officer for Tennessee Valley Authority, where he was responsible for TVA's government relations, customer relations, and economic development. Mr. Manning earned a Bachelor of Science in Electrical Engineering from North Carolina State University and holds a Master of Business Administration from Queens College. At this point, I will turn it over to Rob Manning.
Thank you very much. I appreciate that introduction, and thank you for the opportunity this afternoon for everyone on the call to talk some about the work EPRI is doing in EMP space. This has been a particular interest to me. I started working on EMP when I was at TVA as early as 2008 or so, and have been working diligently on this issue since that time. And it's been quite a challenge because, as John said, it's difficult to get to information, and then when we do get it, it's hard to understand how it applies specifically to the utility industry and our electric infrastructure protection. So that's kind of the underpinning of why we wanted to go after a work around EMP. We basically want to inform risk analysis. We want to provide a solid technical basis for decision making. And the fact that I get to talk with all of you today is very much aligned with our goals and objectives to do just that. In case you're not familiar with, I got to figure out how to make my slide go forward. There it goes. In case you're not familiar with EPRI, most of you probably are. We're now about 45 years old. We are a nonprofit. Not everyone understands and knows that EPRI is a 501c3. We're created for the good of society, and we have probably some of the same missions that most of you have, and that's safe, reliable, affordable, environmentally responsible electricity for people all around the world. So we share in that in a large sense, and of course EMP is an important, managing EMP is an important part of that consideration. And EMP is not something that's new. As John mentioned, we've been working on this for a long time. In fact, we've been testing since the 1950s, and actually did experience an impact in 1962 associated with the Starfish Prime nuclear test, which created some challenges in the state of Hawaii, which we spent a lot of time and energy trying to learn from that and apply those lessons learned going forward. And it's become more and more and more pertinent to us in this day and time as we've extended our reliance on more digital equipment and less analog traditional equipment. As we've done so, we've increased our exposure to an EMP like attack. So I thought I would do a bit of a base informer on EMP. I expect many of you are perhaps well read on this topic, but just to make sure we're all on the same page, I'll go back to John mentioned E1, E2, E3 to talk just very, very quickly about what is an electromagnetic pulse. There are naturally occurring electromagnetic pulses, or EMPs, which are largely emanate from the solar flare initiative, and we've labeled those as geomagnetic disturbances. You may have heard them called GMD. But of greater concern, perhaps, we spent a lot of time and energy on GMD, and we've made a lot of progress on GMD. That's not necessarily the case on man-made EMP, which can come from a couple of different scenarios, but the most complex of which is a nuclear explosion. And this nuclear explosion creates an X-ray, a gamma wave, which interacts with the atmosphere of the Earth and the Earth's magnetic field, and it creates this wave of energy that looks like the graphic on the lower right, which is kind of a three-pronged wave of energy, each of those prongs with a different characteristic, which we have labeled E1, E2, and E3. And it's important for us to understand how each of these interact with the electric system independently, but also how do they link together and create situations that we have to deal with on the electric system at the same time. Sorry, I figured out how to go backwards, but not forward. So one of our greatest concerns in this day and time is high altitude burst EMP, which would be a nuclear weapon detonated, or an EMP weapon detonated at an altitude above the continental United States that would increase the reach of the device. It's essentially limited by the horizon. So the higher up you get, the broader the reach of the device. So something that's detonated at 400 to 500 kilometers over the central United States could potentially, depending on the location of the Earth's magnetic field and the blast and the size of the blast, but it could potentially have an impact over the entire United States, and certainly across a single electric interconnect of the 3 electric interconnects in the United States. So we are predominantly concerned about high altitude burst EMP, or HEMP, and that's been the subject and the target of much of our research to this point. There is a lot that we do not know about EMP. I kind of summarized that here on this slide. With E1, E1 is a huge wave of energy that occurs very, very quickly. It's a nanosecond type speed, but the energy level is so very high that while it probably is too fast to flash over on highly insulated equipment such as transmission system, control systems, SCADA systems, communication systems are not as well insulated, and that level of energy, even for nanoseconds, is likely to create damage and could very well create fatal damage to those types of components. Still some work that needs to be done there. We have a lot to learn around E1, but in large part, we think of that as a digital attack. When E1 occurs, it will knock out control systems, protection systems, the kinds of things that ensure that our system stays up and running. The E2 wave is a bit like lightning. It's a little different from lightning, but it has enough characteristics that are similar to lightning that we believe, we haven't tested that unequivocally, but we believe that the E2 wave will actually, we will have a certain amount of protection from E2 because we are already protected in large sense from lightning. And that same protection from lightning will serve to protect us well against E2. We have to study that. We haven't studied that yet, so there's still a good bit of work to be done there. E3 is probably the most complex of the energy phenomena, and it's E3 that bears a resemblance to solar flares, or GMD. With a GMD or a solar flare, you do not have an E1 or an E2 component. You only have the E3 component. But there are some major differences. A solar flare can last for days, for example, and generally the level of energy from a solar flare will be magnitude smaller than a nuclear blast EMP magnitude. So with a nuclear blast, high altitude nuclear blast, we would expect to see E3 that would be very, very high, which would induce would induce very low frequency currents on the electric grid. So much so that the electric grid would interpret these as DC flowing currents. And of course, you know, we have an AC system. So the implications of those DC currents flowing underneath our AC system manifest themselves largely inside equipment that's designed to only operate for AC, and that's largely our transformers. Transformers that we use on our system are alternating current required transformers. And when you insert DC into those transformers, it creates that they get out of symmetry. They're no longer able to operate within the parameters they are designed. We call that, we exceed their half saturation, but it essentially means that they begin to create harmonic disturbances that make their way back onto the system, and they begin to look like a very large inductor to the electric grid, which means they're sucking in reactive power in large quantities. At the same time, this reactive power that's being sucked into the transformers has to go somewhere, and that largely manifests itself in rapid heating of power transformers. And this is where you have seen the scenario in a number of the books that have been written that power transformers will fail all across the grid, and that we will have a wide scale collapse of these really high voltage power transformers around the U.S. So that's exactly why this is where we began our work, looking at the implications of E3 on the power grid, and specifically, I circled it in red there, the extent of bulk system transformer failures. So that's kind of where I wanted to go with this. I'll talk a bit about our project. We initiated a 3-year research project, as John said. We actually started in April of 2016, so we're celebrating our 1-year anniversary in this month. We are largely on schedule at this point. Our objective is to understand the EMP threat holistically. We've been working with John to create a declassified approach so that not only could we share that with electric companies, but we could also share that with regulators and policymakers and stakeholders, such that everyone can understand what the vulnerability of the electric grid would be to EMP, what the impacts could potentially be. We will work towards developing mitigation and hardening techniques, even options for recovery, and all of those together will form a decision support tool that allows us to make really good, well-informed, risk-based decisions on what should be done. So we're very pleased with the level of interest in this project. We have 56 utility members in the United States that are participating in this project, which is certainly one of the highest, if not the highest, that we've had at EPRI on any one particular project. So I would take from that there is dramatic and substantial interest across the United States in providing technical basis for decision making around EMP. That was the intent of our very first public release from this project back in February, that has the very complicated name magnetohydrodynamic electromagnetic pulse is essentially E3. So you could draw a line through all that and say E3 assessment of the U.S. grid. And our objective with this was to look specifically at those large bulk power transformers, that is, transformers in the United States that serve at 69 kV or greater. There's 37,000 of those, not the individual ones that serve customers, but the one that feed the bulk energy system in the United States. So we looked at all 37,000 of those transformers and the associated impacts from E3 that induced this geomagnetic current on the system. So the results of that have been really fascinating. So I wanted to share a bit of our process here. This is just a snapshot of the process that we followed to reach a conclusion. We essentially followed the same methodology that had been used previously in Oak Ridge National Lab study, and a study commissioned by the EMP Commission that was completed by Meditech. We looked at and modeled GIC current flow. That's geomagnetically induced current. That is that DC current that's induced by E3. We modeled that all across the United States, and we moved the blast locations around so that we tested actually 11 different blast locations to see what would happen with geomagnetic currents associated all around the United States. And these little yellow bubbles essentially give you an example feel of what the current levels might be in different of those 37,000 transformers. This is a single blast location, for example, in the U.S. From that, we were able to take the GIC currents and actually calculate the impacts on individual transformers. This is the same approach that had been used in previous studies, but we decided to take that one step further with the EPRI study and reach out to transformer manufacturers and try to gain a better understanding of exactly how does a transformer perform when it's seeing these kinds of high levels of GIC currents flowing through it. And we basically found that we needed to take a time temperature analysis into consideration when looking at this system. So we went back and from manufacturers pulled the most conservative, most frequently used transformer designs in the United States, and we applied those time temperature curves to get an estimate of what would actual transformer heating be associated with those GIC currents. So you could think of it in this way. If you have an electric stove and you turn the oven on, it doesn't instantly reach 350 degrees. It takes it a little time to heat itself up to 350 degrees. And the same thing's true of a transformer. A transformer is very, very large, tremendous amount of metal in the transformer, and a whole lot of oil. And even though you have very high levels of GIC current flowing inside the transformer for a period of time with a nuclear blast E3 for several seconds, 60 minutes to even longer, 60 seconds to even longer, excuse me, you still have a gradual heating of the transformer. It doesn't instantaneously reach its potential temperature. So once we applied that time temperature constant, what we found was that the gradual heating of the transformers had a very substantial impact on the result of overall heating. We were able to go out and grab the IEEE standard on temperature limits for transformers and apply those temperature limits all across the United States. What we discovered was that the IEEE assumptions were that these temperatures were at for transformers in new condition, and I know it will not be surprised to any of you on the phone that transformers in the United States are not at all in new condition. We have a database of some 1,400 of the 37,000, so we do have actual statistics on a very good representative statistical sample of U.S. transformers, and we were able to really put them in three different categories, green, yellow, and red, which are just what you would think that might be. Green transformers are in very good condition. We actually derated the IEEE standards by 10%, lowering the temperature to 180, meaning we would want to highlight it if it came within 10% of maximum temperature if it was in this category. We lowered it again for level 2, which was, I would call that medium range condition transformers. And then the level 3, we lowered it again. And the level 3 transformers were those transformers that are much older or generally, I would say, in poorer conditions. So we have basically good, fair, and poor conditions. And from that, we changed the temperature setting. So essentially, we said if a poor condition transformer, we were able to forecast 140 degrees Celsius in that transformer, that we would begin to see damage to the structural components of that transformer. So that's the basis for our assumption. And this is, while it's a complex slide, I apologize for the complexity on the slide. We basically have summarized all of the process here. We ran every transformer, all 37,000, as category 1 transformers, saying if they were all in good condition, what would the failures be based off a single blast. Then we ran all category 2s, we ran all category 3s, and then we moved the blast around. So we did this 11 different times, and we came up with a number of failures, and then we applied a statistically valid sampling of the condition of the U.S. fleet. For example, a large percentage of transformers fall into category 3. In fact, category 3 is the largest percentage of transformers. So we made the assumption that if our 1,400 transformer database is 50% category 3, then we applied that to all 37,000 transformers. And the ending results of that were really somewhat remarkable given where we are at the state of knowledge right now. The ending results of this was that really we would not expect a large failure rate in these major bulk power transformers. In fact, the lowest number that we achieved was 3 of 37,000 based off a single blast location. The highest number that we reached was 14 based off of a different blast location. So even the worst case scenario for a single blast was 30 out of 37,000 transformers that we would see 14 transformers which would approach that level of damage. It doesn't say that they would actually reach damage, but it does say that they would have temperatures that we should be concerned about for potential damage. So I say all that to say that failure from a large number of bulk power transformers in the hundreds from an E3 seems unlikely based off of this information. So now that we know that, it's time to consider, well, what happens if we also apply E1 and E2 to those transformers at the same time? So we are pursuing that and looking beyond just simple transformer analysis only. So we're looking towards testing E1 and E2 on all transmission and substation components. So that's a rather difficult process. We have to figure out, because this is an atmospheric situation, we have to figure out how does that E1 energy pulse couple itself onto the system. Does it attach itself everywhere there's metal, which is what we would assume? How does it run up and down the line? And how do we model that with mathematical models so that we can then test actual levels of that E1 on particular devices? So we are well underway on developing that modeling at this point. We have 2 labs that we are planning to construct. One has been completed in Knoxville, the second in Charlotte we expect to complete by the end of the year. And we've been developing, meanwhile, some specifications for hardening a transmission control center. And we've been interpreting the mill standard so that we can produce something that utilities could actually take and apply if they wanted to apply the current level of knowledge associated with EMP hardening. The challenge with that, of course, is that to apply the mill standard to every situation would really be very impractical and likely be cost prohibitive. So the mill standard, while it certainly improves our understanding, it's probably not sufficient as a strategy for utilities around the United States. So saying all that, I would say our real challenge is we finished one set of it, and we're 1 year into a 3-year project, and we finished one set of very complex number of research initiatives that need to be done. So while we have some information, the information, while it informs the argument, we're not ready to make a conclusion about that information that utilities should do a certain thing or not do a certain thing based off of this information. I also wanted to share with you that there is a YouTube video that EPRI has produced that's available. Here's the link for that. I think you'll have a copy of the program and can download the link. And it's a pretty extensive interview, about 11 minutes long, which goes into more detail about EMP and how it attaches itself to systems and so forth. So if you have a chance or you have some technical folks that want to look into that, it's a good place to go to try to see more on that. And then I'll just finish up by saying this. HEMP is very, very complex. We are beginning to understand how a nuclear blast at altitude would impact our electric systems, but we really definitely need more study. Now, while we don't expect a large number of bulk power transformers to fail, we have not anticipated the potential voltage collapse associated with the harmonics and the reactive power draw, and we have not properly accounted for the implications on the control systems from an E1 pulse. So there's a lot to be done, and it's just premature to draw any kind of holistic conclusions that are sufficient to develop a broad risk mitigation plans based off of where we have at this point. Nonetheless, we are starting to understand this better. So we're beginning to reach out and find our way to a much better place than we've been historically around not just EMP, but how EMP applies itself onto the electric grid around the United States. So with that, I will stop and turn it back over to whomever for questions.
Okay, thank you, Rob. Do we have any questions, either typed in or raise your hand, and then Shamika will open up your mic. And while you're maybe thinking about that, unless you see some, Shamika, I'll ask one for Rob. as I understand it, the E3, as a result of a nuclear blast, you said worst case about 14 transformers. But if an E1 and an E2 occurred at the same time, then that gets much more interesting, difficult to understand. What practically would have to happen for all of those things to happen at the same time? You may have mentioned this, and I may have missed it, but how would an E1, E2, and E3 all happen at the same time?
It would require a nuclear blast, so it would be a nuclear weapon that would be detonated. You will automatically get E1, E2, E3 following a nuclear detonation, particularly in the atmosphere. If it's underground, not so much so, but if it's in the atmosphere, you would definitely see E1, E2, E3 all occurring within E1's a nanosecond, E2 is a microsecond, E3 is a second basis. So they are sequential. They do kind of follow one another. But just by contrast, a weaponized EMP, or the small kind of, people think of them as suitcase devices, they're actually much larger than that, but targeted EMP weapons, or sometimes called intentional EMI or electromagnetic interference weapons, only have an E1 pulse. There is no E3. There is no E2 on a electromagnetic weapon. But a solar flare only has the E3 component. So while a solar flare can generate very long periods of heating, it's like leaving your oven on 200 for 6 days. You know, that creates more pronounced heating in the transformers because of the duration. The levels of energy are much lower with G3, and there is no E3, and there is no E1 component to that. So you wouldn't expect to see digital failures as a result of that. So each of these require their own analysis and their own situation consideration, because they're all very, very different.
Great. I have two typed questions. The first is from Alex Morrissey. Are you planning to analyze the E3 impact to the 13,000 high voltage transformers when experiencing a GMD, which would last over hours or days, thus increasing the temperature and potential damage to the unit?
Yes, we have done that using our model already, and it depends on the size of the solar flare. So much is different with GMD. With GMD, many of your companies have the opportunity to initiate operational changes. Simply taking a transformer offline would be sufficient to protect it. So if you started to see transformer heating occur in a solar flare, then you can kill the power at that transformer, and it'll solve the problem. So it'll prevent the damage. So we kind of treat that differently. Plus, we have an excellent monitoring system that's tracking solar flare activity. We'll know in advance. The utilities are now participating in a network that's sharing GIC currents flowing across the system. We have sensor capabilities so that we know what those GIC currents are. We have transformer heat monitors, so we know what those monitors are telling us about transformer heat. So we're just in far better position on geomagnetic events than we are in EMP. Not only because we know what to do, but we've already begun to put, NERC has a standard out now on GMD. We've already begun to put a lot of mitigation effects out there into application.
Great. So we have another question from Fred Hoover. How does the size of the bomb affect the impact of the EMP effect?
That's probably a good John Ostrich question, if he can answer it.
Okay, yeah, can you hear me? My computer died, but my phone's still working.
Yeah, it's working.
Okay.
Yes.
That's a good question. Generally, the yield does make a difference for the E3 impact. So the larger the bomb, the larger the area, as well as the larger the impact for the E3. The yield does not really matter much for the E1. So if you have a small bomb and you put it up at the right altitude, you can cover the continent with a pretty good E1 whack. But E3, if you have a smaller bomb, is not going to cause as much damage. It might just be regionally. So that's important to know. You know, we're really looking at the grid and really worried about the E3 was the first, you know, point that that EPRI looked at. And a smaller weapon isn't going to do as much. And EPRI was very conservative in their study. You know, it might not be noticeable to most of you, but it was a 1.4 megaton bomb is the explosion that they took. That's a very large thermonuclear weapon, and very few countries have that.
So I don't have any other typed questions. Does anyone have any questions that they want to ask directly? If you do, please use the raise your hand function, and I can unmute your phone. All right, David, doesn't look like we have any other questions.
Okay, well, I want to thank everyone for joining us, and especially thank our two presenters for great presentations. At this time, we will go ahead and close out the webinar. Thanks again, everyone.
Okay, thank you.
Thank you.
Bye.